Hello everybody. So, by this time what are the things that we have covered? We have covered the introduction part, the first law and the second law. Before we proceed further, I would like to do a few problems on these particular topics and then proceed. And the problems which I will be dealing with today, they will be primarily confined to the things which we have already covered, and I would also like to mention that the assignments along with these problems will be consulted while preparing the question papers for your final examination. Now, let us go to the first problem here. Let us see what the first problem is. The first problem is that well, there are three properties of the system, right. One property is, say, it can be PVT or anything. The first property, say, is Z, and we have expressed Z as a function of two other properties x and y. Just to keep matters general, I have mentioned these as Z, x and y. They can be PVT, they can be something. Now, the thing is that we know that x and y are properties of the system, right, and this is the equation of state of the system, the equation of state which relates Z with x and y. And there is, we have mentioned one particular equation of state, we have mentioned one particular equation of state. And what is it given? It is given that whether this particular functional form is fine if all the three parameters x, y and z have to be properties of the system. How do you go about it? We know that an equation of state relates the different properties of the system. How do we define properties? If you recall one of my slides, you will see that we had defined properties of the system as the characteristic of a system which is associated with energy and its transformation, and we had mentioned a few features of the system. What is it? Firstly, it should have a definite value when the system is in a particular state. It should be determinable irrespective of how the system is brought to that particular state, or in other words, it is independent of the path followed in moving from one state to the other. It depends upon the initial state and the final state. So, therefore, suppose I write down dz equals to, say, it is a function of x and y. So, it should be del z del x at constant y dx plus del x del y at constant x dy, right. Now, where this should be an exact, since it is an exact differential, we can always write it down as m dx plus m n dy, where m is del z del x at constant y, n is del z del y at constant x. Now, suppose we double differentiate this equation. So, in that case, suppose we are differentiating it in the form del del y of del z del x at constant y. This should be equal to del del x of del z del y at constant x. This is at constant y, this is at constant x. It should hardly matter whether we are differentiating z with x first or with y first, or in other words, both the things del 2 z del y del x should be equal to del 2 z del x del y, isn't it? If this has to hold true, only then we can say that z is a property of the system. Now, for this to hold true, what does it imply? It implies that del m del y at constant x should be equal to del n del x at constant y. So, what do we need to know? The equation which has been proposed in this particular case, the equation is x y dx plus y square dy. So, therefore, this is nothing but m, we have denoted this as m, this as n. So, what do we require to do in order to find out whether z is a property? For z to be a property, dz has to be an exact differential. If dz is an exact differential, then the order of differentiating z with respect to x and y is not going to matter. Del 2z del y del x should be equal to del 2z del x del y, and this automatically implies that del m del y at constant x should be equal to del n del x at constant y. So, for the equation of state which is provided, we just need to verify this particular thing. Once we verify this, we find that this holds true, then we can always say that this particular equation of state is thermodynamically consistent. So, let us see what is del z del m del x at constant y under this particular condition. Here we find that del m del y at constant x, this is nothing but equal to x, right, and what is del n del y at del m del x at constant y, this is equal to y square. So, therefore, we find that this is not equal to this, and therefore, this is not a proper equation of state, or this is not a proper functional form between x, y and z in order to ensure that z is a property. So, therefore, what is the next question? What will be a proper functional form? Now, in order to get a proper functional form, we need to suggest corrections either in m or in n or in both, such that this equation is valid. Now, this can be done in a number of ways. For example, suppose I suggest, or suppose we propose that m is equal to say x y cube, n is equal to x square y square. I have changed both of them. Now, for this particular situation, what is del m del x del y at constant x? Let us see. This is nothing but equals to 2xy square. Let me write it in a different pen. If we propose m equals to xy cube, n equals to x square y square, for that case we find del m del y at constant x is going to be 2xy square. Similarly, del n del x at constant y is also going to be 2xy square. So, therefore, this can be one particular equation of state relating x, y and z. We have obtained this by modifying both the terms. So, therefore, a correct equation of state in this case can be xy cube dx plus x square y square dy. But please remember, this is not the only equation of state that we can use. We can use some other equation of state as well. For example, suppose we suggest that dz equals to y cube by 3 plus y square dy. What do we get in this particular case? We get del m del y at constant x is equals to y square, del n del x at constant y equals to y square. So, therefore, this can also be an equation of state where we have just modified one term and kept the other term. This term is kept constant, only this term has been changed. In the same way, we can also write it down as say xy dx plus x square by 2 dy. So, this can also be an equation of state, right. So, therefore, we find that for any particular property, it is important to remember that the differential has to be an exact differential, and if you recall, I had repeatedly requested you, in order to differentiate between exact and inexact differentials. Exact differentials I had shown by d, inexact differentials by a cut d, dq dw in this way, du in this way. You can very well understand the difference. While this depends upon the path, this is just a state function. So, therefore, it is immaterial how we perform this u. It is just important that the initial and final states are the same, and the equation of state, there cannot be any one equation of state connecting the three variables. This can be one equation of state, this can be one equation of state where I have just changed one parameter, and along with that this can also be an equation of state. this can also be an equation of state. So, therefore, this is one thing which I wanted to emphasize upon, that how you are going to find out whether any equation of state is thermodynamically consistent or not. Now, let us go to the second problem. What is the second problem? We have expressed internal energy, or rather to be more specific, it's wrongly written, it is the specific internal energy. I am sorry about it. It should be the it should be the specific internal energy. So, therefore, we have an equation relating the specific internal energy with the temperature, which automatically it suggests us number of things. The first thing is internal energy is a function of temperature only in this particular case, and the equation of state for that particular fluid, mind it, it is not specified that it is a gas or a liquid, it is just a fluid. The equation of the state for that particular fluid is also suggested. If you find the equation of state, it is something of PV equals to a constant into T, right, but the constant is not equal to R in this case. So, therefore, it possibly is not an ideal gas, but it can be represented by an equation of state for a gas. And we also observe that since it is PV equals to say Ct or C1T. So, therefore, since it resembles the equation of state of a gas, that is why U has been expressed in this case as a function of temperature only. Now, what are you required to find out here? You are first required to find out Cp and Cv for this particular gas or for this particular fluid, and then you are supposed to compute some change of state for this particular fluid from some initial state to some final state. What is the initial state? The pressure of the initial state is given, it is 1 MPa, and the temperature of the initial state is given. The final pressure P2 is also given, and what are you required to find out? In going from this state to this state, you are required to find out the work done and the energy change in this particular process. It is delta E, but for this case delta E will be equal to delta U. So, therefore, and since it is given that it is an adiabatic process, so we know for this particular process Q equals to 0, and therefore, we know from first law W will be equal to delta U or delta E in this particular case. So, therefore, we find that the problem reduces to finding either W or delta U, right. Now, there is a small thing which you need to consider, delta U equals to Q minus W from our sign convention. If you follow our sign convention, then in that case your W will be equal to minus of delta U or delta U will be equal to minus of W. This you need to keep into consideration. So, for this particular change in state, the T2 is not given. So, you can compute either the delta U or you can compute the work done. If you find one, you need to find the other. In order to compute this particular change in state, what is given? You have the equation of state and you have a relationship relating the specific internal energy with the temperature. You have these two things in mind. If you observe the equation of state, you find that T is in degrees per centigrade, which automatically implies that this is nothing but the absolute temperature of the system. Now, we can do the first part first, or even if the first part is not given, you will find that unless you find out Cp or Cv, one of them, it is difficult for you to compute the second part. So, first let us concentrate on the first part, and then we will see how the information we have gathered from the first part helps us to find out or solve the second part of the problem. What is given here? Let me write it down. It is given U equals to 178 plus 0.718 T in degree centigrade. You need to find out Cv in this particular case. By definition, what is the specific heat at constant volume? We know that for most of the cases Cp will not be equal to Cv. If we knew that it was an ideal gas, we could have found out Cv and we could have computed Cp as Cv plus R. In this case, it is difficult to do because we do not know, rather this equation is not an ideal gas equation, as is quite evident. So, therefore, in this particular case we cannot use this particular, in this case this equation is not going to be applicable. How to find out Cv? Cv by definition is del U del T at constant V, isn't it? So, therefore, if we differentiate this equation with respect to T, what do we get? We get 0.718 kilojoules per kg degree Kelvin. Whether it is going to be kg or moles or whether it is going to be joules or calories, that all depends upon the units in which U and T has been specified. In this particular case, if you observe, we find that the specific internal energy has been specified in terms of this kilojoules per kg, T is in degree centigrade. So, the unit of Cv is as given. How to find out Cp? What is Cp by definition? Del H del T at constant P. What is this H? This is nothing but equals to U plus PV, right. What is, if from the problem, what is U? U is nothing but equals to 178 plus 0.718 T. What is PV equals to? This is going to be 0.267 into T plus 273. So, therefore, from this equation, can you not express H in terms of temperature? What is the equation? I will just write down here. In this particular equation, we find H is nothing but equals to 250.891 plus 0.985 T, isn't it? So, therefore, from here we can find out that H, if you differentiate H with respect to T, what do you get? You get the Cp value. So, in this particular case, what is the Cp value that you are getting? Cp, which is nothing but equal to del H del T at constant P. Please remember, small t is for degree centigrade, capital T is for degree Kelvin. From here we get this to be 0.985 kilojoules per kg Kelvin. There is another interesting thing that I would like to mention in this particular case. You will notice that in this particular case, what is Cp minus Cv equals to? Cp minus Cv, if you subtract one from the other, what do you get? You get this is equal to, sorry, very sorry, Cv was equals to, very sorry, your Cv was equal to 0.718. So, this is 7, this is 6, this is 2, it is 0.267. What is this 0.267? Just refer to this problem, you find this is the constant C1T, which would have corresponded to R for an ideal gas equation. So, therefore, what does it imply? It implies that if you have a equation of PV equals to C1T, then in this particular case, Cp minus Cv will always be equal to the constant which is C1. For an ideal gas, this constant C1 reduces to R, right. But here the very common tendency which I find among students is they just see that acha, you have to find out Cp Cv, U is given. So, they find out Cv and then they simply add it up with R and try to find out Cp. But they do not notice that that is applicable only for an ideal gas and for no other situation. Now, let us come up to the next part of the problem. Now, for this part of the problem, there are initial conditions given, final conditions given, the process is specified. What is the process? The process occurs according to this particular equation, right. And what is this equation? This equation, as you know, this equation is for a polytropic process, isn't it? It's already mentioned, it is adiabatic. So, it is an adiabatic polytropic process that we are going to deal with this. Fine. So, for this process, if you know P1 V1 to the power 1.2 should be equals to P2 V2 to the power 1.2. The initial conditions are given, you need to find out the final conditions. But if you wish to use this equation, you find the equation is in terms of PV, whereas initial conditions are given in terms of P and T, which is quite understandable, as I have already mentioned that pressure and temperature are the easily measurable and more accurately measurable variables. So, for that, what do you need to do? You simply need to convert or express V in terms of T, and for that you need to use this particular equation. So, therefore, how do we go about this then? We know that PV equals to 0.267 into capital T say. Okay, I just make it for convenience. So, P1 0.267 T1 by P1 to the power 1.2 should be equals to P2 0.267 by P2 into T2 whole to the power 1.2. So, this equation, by this equation I could actually relate the pressure temperature of state 1 to the pressure temperature of state 2. I can solve this out and I can find out the temperature T, it comes out to be 49.25. The temperature in degree centigrade comes out to be 49.25 degree centigrade. So, once I know this, and I can always compute delta U for this particular case. What is it? It is m CV dt, right, integral of this, or in other words, since CV remains constant, so it is T2 minus T1. M you already know, it is given 2 kgs. CV you have already found out from the previous problem, it is 0.718. You know T2 by this time, you know T1 by this time. So, therefore, it is 49.25 minus 200, which gives you minus 216.48 kilojoules. As a result, you know W, it is nothing but equals to minus of delta U, which is nothing but equals to 206.48 kilojoules. Now, this is one particular process of doing it. You can also do it by first computing W and then computing U. That can also be done. You know that the process is an adiabatic polytropic process. Now, if you recall that when we were discussing these particular things, I had already discussed the PVT work in various quasi-static processes. I had discussed PVT work for an isobaric, isochoric, isothermal and an adiabatic process. In fact, this is specifically not an adiabatic process, this is a polytropic process. It becomes adiabatic when this n becomes equal to gamma, right. So, can we not use this particular equation here in order to find out if we can use this particular equation here, this particular equation, this is the equation. So, can we not use this particular equation in order to find out W? We can do it, right, but again in order to use this equation, you know P1, you do not know V1. So, you again have to express V1 in terms of temperature. Your V1 in this particular case I have already written down. Your V1 is nothing but this part, isn't it? So, therefore, you can substitute V1, n is nothing but 1.2, P2 and P1 both are known to you. So, therefore, you can find out W in this case and equate this W with delta U. I give it as an exercise to find out W independently from this equation and compare the value with the W which you have obtained by equating this with delta U, just to show that once the path is specified, no matter how you do the computation, the work done will be the same for both the cases. Now, we move on to the third problem. Let us see for the third problem is. This is also another problem in order of where we perform some particular change of state, and from that particular change of state we try to find out the heat interactions, and with that one additional thing also we would like to find out in this particular case, the entropy change, right. What is the process that we have devised? This is a system is an ideal gas, and for an ideal gas, what is the process? It is a reversible isothermal expansion. So, if it is a reversible isothermal expansion, what does it imply? It implies that the change of state, it will be the from P1 V1 T to say P2 V2 T, isn't it? And for this particular change of state, since it is an ideal gas, we know that since T remains constant for an isothermal process, du is equal to 0. So, therefore, for this process we know dq is going to be equal to dw. So, therefore, to find the heat interactions, we can find out the work done. From the work done, we can find out the heat interactions. For an isothermal process, again if we go back to the equations which I had shown, for an isothermal process Pv equals to constant, and this is the expression for the work done, isn't it? So, therefore, in this particular case P1 V1 is nothing but equals to RT1. So, therefore, this can also be written down as RT1 ln P1 by P2. Agreed? So, therefore, we can find out the work done, and this will be equal to the heat interactions under this particular process. So, accordingly, in order to find out the heat interactions for reversible isothermal expansion ideal gas, we have already got the expressions, we had already derived the expressions. So, for this particular case, your dW reversible was equal to, as I have shown you, it was nRT1 ln P1 by P2, or else you can also write it down as nRT1 ln V2 by V1. Right. We know that ideal gas du equals to 0. So, therefore, dq reversible will be equal to dw reversible will be equal to nRT1 ln V2 by V1, right. But here we are required to find out the entropy change as well. If you recollect what is ds, it is nothing but equal to dq reversible by T. In this particular case, T remains constant. So, therefore, in this case we can, if we substitute it, we find out that this is nRT1 by T1V dV, which is nothing but equal to, if you integrate this particular equation, say from state 1 to state 2, say S1 to S2, or in other words just from state 1 to state 2, we need to integrate this also from state 1 to state 2. So, therefore, this gives us nR ln V2 by V1. This is equals to delta S for this particular process, right. But this was pretty simple, but the problem does not end here. We are required to find out the heat interactions and the entropy changes for two other processes which, provided the initial and final states are the same. What are the two other processes? The two other processes are isobaric expansion followed by isochoric cooling, adiabatic expansion followed by isochoric heating, and all the processes have to be reversible. So, if we just plot it simply for ease of your visualization, this was state 1, this was state 2, this was the process which we performed, this was P1 V1, this was P2 V2, say T1, here also it was T1. This process we have already performed and we have found out the heat interactions and the entropy changes in for this particular case. This is say process A. What is process B? Isobaric expansion. So, that means pressure remains constant. This is isobaric expansion followed by isochoric cooling, right. So, the process B is you proceed in this way and you proceed in this way. Now, for this particular process, it comprises of two processes, say B1 and B2. For this particular B1 plus B2, we can very well write down dq reversible along B1. What is this? This is du plus dw reversible along B1. What is du in this particular case? This is an isobar, this is du is going to be Cv dt plus dq reversible under this case. So, therefore, this is going to be P1 dV, isn't it? So, therefore, q reversible along B1, this is going to be your integral, and here if I specify the states, it is going to be P1, all of these are small, they are molar, P1 V2 and say T3. So, therefore, I can, this has to be integrated from T1 to T3 Cv dt plus P1 V2 minus V1, agreed. So, this is the q reversible for this particular path. What is dq reversible for B2? In this particular case, we have integral T3 to T1 Cv dt. Since this is an isochoric process, so naturally dV equals to 0. So, naturally dW reversible, which is equals to P dV, will be equals to 0, right. So, therefore, in this particular case, what do we have? We have dq reversible equals to du. So, therefore, automatically we find that when such a situation arises, the heat interaction behaves or can be evaluated from this as a state function as it is. So, now what is dq reversible for the entire process B1 plus B2? You add this and this with this. When you add, you find that in this case the integration was performed from T1 to T3, in this case it is performed from T3 to T1. So, therefore, since we are just the initial and final states are the same, we are just reversing it. So, therefore, these two cancel out and we find this is equals to P1 into V2 minus V1. I am sorry, I am repeatedly writing it as capital. So, therefore, this is dq reversible. What is the entropy change now? Let us see. Entropy change ds along B1, it is going to be integral of, sorry, this integral, this is dq reversible by T along B1, right. So, therefore, dq reversible T along B1, I need to integrate this, I need to integrate this. So, therefore, what does it amount to? T1 to T3 Cv dt by T plus nr integral V1 to V2 dV by V, agreed, which is nothing but equals to T1 to T3 Cv dt by T plus nr ln V2 by V1. What is ds along B2, tell me? This is nothing but T3 to T1 Cv dt by T, right. Now, add this particular ds and this particular ds to get the delta S along path B1 plus B2. What is this? This is equals to nr ln V2 by V1. Compare this with the delta S that you had obtained for an isothermal process. What do you find? You find that the delta S for both the cases are the same, but we find that the dq for this process and the dq for this process, they are not the same. Again you can repeat it for the next process which is given. The next process is nothing but your adiabatic expansion. So, for the next process what is it? This is basically the adiabatic expansion followed by the isochoric heating. So, therefore, here we start from P1 V1 T1 along a process say C1 to arrive to P3 V2 T2, and then from there we come to this process. For this process also we can proceed. I believe you could have done it on your own, but suppose we work it out, say dq reversible along C1, that is equal to 0 because it is adiabatic. So, therefore, ds along this process it is going to be 0. dq reversible along C2 is nothing but du which is equal to Cv dt. Again, since for an isochoric process dw equals to 0, I have already told you. So, therefore, what is q reversible along C1 plus C2? It is just Cv dt, right. What is ds for this process? Let us see. This is going to be integral T2 to T1 Cv dt by T, right. And we can also for this particular path C1, say for this particular path C1, we can also write that Cv dt equals to minus nRT dV by V. Why? Because du equals to minus W since dq equals to 0, right. So, therefore, instead of the Cv dt by T, can we not substitute it with minus V1 by V2 nR dV by V, which gives us nR minus nR ln V2 by, this particular case there was a minus, very sorry, so it becomes a plus. So, therefore, this is ds in this particular case, right. Again if we compare the q reversible and the ds's, what do we find? I can just superimpose it on this, and if you observe all the three, what do you find? For the path, for this particular path it is nR ln V2 by V1. For this path it is nR ln V2 by V1. In this case also it is the same, which automatically implies delta S is a property of the system, and no matter what path we follow, provided the paths are reversible, we know that delta S it is going to be the same, provided the paths are reversible. On the contrary, we find delta S from this particular formula, that ds equals to we find it from this particular formula, but here even if you are finding it from a path function, it is a property, but the heat computed for all the three cases, this is for case 1, this is for case 2, and this is for case 3. This is for case 3, we find that the heat interactions along the three paths, they are different, although the entropy change is the same for all the three. Thank you very much, and I look forward to further interactions while we proceed in this particular course. Thank you.